This is Pre-Calculus, Section 3.5 Notes, Part 2. So I just wanted to review the very last part of the problem that we were working on at the end of the last video. I was taking that negative sign in front of the nested parenthesis and I was distributing it to simplify to write my final answer. So by the complete factorization theorem, P of x is going to be equal to x minus 3 minus I times x minus 3 plus I. And that is how we write this polynomial in its complete factored form. We had to find the solutions first before we could write the factors because its solutions were imaginary. Next, we're going to talk about the conjugate zero theorem, which I actually already mentioned earlier in this section of notes. I just didn't call it that. So the conjugate zero theorem says that if a polynomial p of x has real coefficients, then complex zeros come in conjugate pairs. I mentioned earlier that you always have an even number of imaginary solutions, and that's because they always come in conjugate pairs. Meaning, if 3 plus I is a zero to a polynomial, then so is 3 minus I. Okay, they always go together. So if we want to find a polynomial with integer coefficients that satisfies the given conditions, we're going to use the conjugate zero theorem. Because for our example, they're telling us that p of x has a degree 3, which means it has 3 zeros, yet they only tell us that it has zeros 5 and 4i. Okay, so the hint here is we have to decide what the third zero is. Well, we know that by the conjugate zero theorem, if positive 4i is a solution, then our third zero that they didn't give us, tricky, has to be negative 4i. Okay, so if we just want to write this polynomial out in using the fact that the zeros are 5, 4i, and negative 4i, my first step is it's going to look like this. P of x equals x minus 5 times x minus 4i times x plus 4i, because again, my three solutions are positive 5, positive 4i, and negative 4i. And now I just have to FOIL this out, but I'm going to put a little note here. We should always FOIL the complex factors first. The math is so much easier if you do it that way. So we are going to start by FOILing these two. And remember, when we FOIL complex conjugates, our inners and our outers are going to cancel. Okay, so we can show it here. We're going to get x squared, and then we're going to get positive 4ix, and we're going to get negative 4ix, and then our lasts are going to give us negative 16i squared. So we really don't ever, when we FOIL complex conjugates, we can just ignore the outers and the inners and just do the full, just do the first and the last. So we end up here with x squared, and then remember, this is negative 16 times negative 1, which gives us positive 16. Bring down that x minus 5, and now we FOIL again. So our answer is going to be P of x equals x cubed minus 5x squared plus 16x minus 80. So the last thing that we're going to talk about, kind of putting some information from our previous section together with some of the information from this section, is counting all of our real and imaginary zeros. So we have a polynomial here, and it says, without factoring, determine how many positive real zeros, negative real zeros, and imaginary zeros the following polynomial could have. So we are not asked to solve. We're just asked to basically make a table of possibilities, and you will see a problem like this on your test. So we know that P of x is a fourth degree polynomial, so that tells us that we are going to have 4 complex zeros. Some may be real, some may be imaginary, some may be positive, some may be negative. We're not sure yet. So the next thing I'm going to do is I'm going to go back to Descartes' rule of signs, and I'm going to determine the possibilities for positive real zeros and the possibilities for negative real zeros. So remember, Descartes' rule of signs says that for positive real zeros, we simply look at the sign changes that are present in the polynomial as it is. My first term is positive, my second term is positive, my third, fourth, and fifth terms are all negative. So based on that, I have just one sign change, which tells me that I have one positive real zero. So I can go ahead right now and I can put 1 in my table under positive real zeros because for sure there's one positive real zero. There's no ifs, ands, or buts about it. Now to find my negative real zeros, this one's a little harder. I have to substitute negative x in each term for x in the equation, and then I'm going to have to simplify, and then I'm going to look at my sign changes. So my first term is going to be positive. My second term will be negative. My third term, negative x squared, becomes positive. Positive times the negative 12, that's negative. My third term, negative 3 times negative x, will become positive. And then my last term is negative. So it looks like I have one sign change here, one sign change here, one sign change here. Since I have 3 sign changes, that tells me that either I'm going to have 3 or, remember, subtract 2 from it. 3 minus 2 is 1. Or 1 negative real zero. So all the possibilities here, I could have 3 real zeros or I could have 1 negative real zero. Well, if my total zeros have to be 4 in either case, if I have the top situation, if I have 1 positive real zero and 3 negative real zeros, that means that I'm going to have 0 imaginaries. But if I have the second situation where I have 1 positive and I have 1 negative and there's 4 total, that means that 2 of my imaginary zeros, or 2 of my zeros would have to be imaginary. And remember, I'm going to put this little note here. These are always going to come in even quantities, because we are always going to have pairs for our imaginary zeros. So they're always going to come in even quantities. So you should never have an odd number in your imaginary zeros column.